Hi everyone. My name is Isabella. Thanks, Carolyn, for the introduction. I'm also honored to be one of Růžena's PhD students. And today I'll be talking about 3D deformable object manipulation and also some soft tactile sensing for industry and manufacturing. Okay, so today we're going to talk about two different things. The first is some work in simulating 3D deformable objects for grasping and how that transfers to real life. And secondly, we'll talk about soft tactile sensing and some applications to industry that I think might be relevant in the future. So let's start with 3D deformable objects. As you all know, they are ubiquitous in life and also in industry. When we think of grasping 3D deformable objects, we as humans actually also have very different strategies depending on the task itself. So let's look at some examples, many of which you might be able to find in an industrial setting as well. For example, when packing food in the food industry, we often face delicate fruits like this. And we want to actually, in this case, avoid grasping it in a way that would bruise the fruit by applying too much deformation, because then it wouldn't sell. And when grasping deformable containers, for example, those that contain food, it's possible to crush the contents inside. For example, for this Cheez-It box, I would avoid grasping it by the face because that would crush the contents. But if the box were rigid, it wouldn't deform to my grasp and I could grasp it in that way safely. Another really popular example these days is robotic surgery of soft tissues. When we do robotic surgery, we want to make sure to grab the tissue in a way that will allow us to maneuver it, for example, to stretch it or prepare it for suturing or other medical procedures. And sometimes in life and in industry, the grasp just doesn't matter. For example, this teddy bear is really easy to pick up. It's actually much easier to pick up this version of a teddy bear than a rigid version of it. So that would become an easy task. So it became clear to us that choosing best grasps for 3D deformable objects is object-dependent and task-dependent. And since these grasp goals are so diverse, we wanted to launch a full-scale simulation study of how these objects respond to different grasps. Now, we say that this full-scale study is best performed in simulation for several key reasons. First of all, deformable objects have infinite degrees of freedom. And so therefore, they're best described by continuous field quantities such as deformation and stress fields. These quantities are also impossible to measure in real life, as I'm sure you know, not only in real life, but in real time. But this can be done in simulation. And finally, simulation can lead to safe experiments that are repeatable, and so are great for planning strategies before you do it in a factory or in the real life. So to respond to basically how useful simulation can be for grasp planning, we present a work called DefGrasp Sim, which enables automatic and systematic evaluation of grasp outcomes for grasps on general 3D deformable objects. And we contribute two key things. First, we release a new data set of 3D deformable objects, which is actually the largest in existence at only 34 objects. This is actually tiny compared to the millions of rigid CAD models that are out there, but this is a start. Then we use the NVIDIA Isaac GEM simulator that simulates deformable interactions using 3D finite element method to create a code base that allows users to run grasp experiments on any object of their choice. And this is what using it looks like. First, you can choose any object, not even one that's restricted to our data set. And then you can run a grasp experiment on that object and record the outcome of that grasp. For example, these outcomes may include the final stress or the final deformation field, or maybe what the total deformation of the object looks like under reorientation of the gripper caused by gravity, or simply whether it was picked up successfully or not. Users can also design custom grasp measures that they're interested in, because at each step of the simulation, you have access to a full state tensor that includes nodal positions, element stress tensors, contact points, and contact forces. Now, the natural next question to ask is, well, do these actually have good correspondence with the real world? To answer that question, we performed a few pilot sim-to-real studies where material parameters are only roughly estimated based on typical values. So there's no fine-tuning of simulation parameters, but yet we still see good qualitative correspondence to the real world. So let's watch a video of what that looks like. So we used DefGrasp Sim to estimate the stresses imparted on a piece of tofu during grasping, which you may see in a food handling factory. So first thing you notice is that qualitatively, the deformation of the tofu matches pretty well, both in real life on the left and in simulation on the right. We also wanted to make it a little more quantitative and predict where breaking would occur. And according to literature, that breaking stress occurs at around 3,000 pascals. So simulation says that under grasp A, no breaking should occur. All the stresses are underneath that threshold. And we verified that in the real world, there was no breaking. Under grasp B, we see that the outlines are higher stress and that breaking should occur at the gripper edges where there's more curvature discontinuity. And as you can see, the exact sort of breakage pattern does occur in real life, as you can tell by the outline of the gripper shown there. And lastly, for grasp C, we estimate in simulation that very high stresses should occur at the points of contact and along the long axis of the tofu. And if you saw that, there was kind of breaking along that axis. So it's quite cool that you can sort of get an idea of how objects will react to different grasps. Another example is that we can kind of find good matching in deformation when picking up this rubber tube, for example. Yeah. There are more of these examples in our paper if you'd like to take a look. Okay, so I want to mention one major shortcoming of this tool, and that it is very slow. This is because it uses the computationally intensive finite element method. In fact, one of these grasp tests can take as long as 5 minutes, especially if the object mesh is very dense and high resolution. So this would not be suitable for online grasp planning. We don't want to wait for hours before we choose which grasp to execute. So the next thing we tried to do is to speed this up. So instead of using FEM as the backend for the simulator, we explore using a deep neural network instead that would expedite the prediction process. Okay, when grasping a 3D deformable object, the most important quantities are typically stress and deformation fields because that would affect the permanent state of the object. So we can get these quantities already using simulation in Isaac Gym, but we wanted to see if we could get similar results using machine learning. So there are also two main benefits of using deep learning instead using a neural network. For one, it's much faster. We're finding that a full rollout takes about 1 second using deep learning, but up to 2 minutes using the FEM simulator. So now that would actually allow us to predict grasps in real time and do online grasp planning. Secondly, neural networks are differentiable. So therefore, we could actually use it to optimize over an initial grasp pose to produce the best grasp outcome, let's say to minimize stress or maximize deformation, for example. This optimization is something that we can't do in FEM. You'd have to use a differentiable simulator. Now, using deep learning, we have an example of what predictions do look like. In this visualization, the ground truth simulated by FEM is on the left, and on the right is the results using deep learning. This object is a rectangular prism. We're plotting only the nodes of that mesh, and then the two blocks are the gripper fingers that squeeze the object in between. So as you can see that as the gripper squeezes, the deformation of the rectangular prism object kind of increases near the grippers. And also the nodes are increasing in stress because there's more force being applied as you squeeze more. And we can see that there's pretty good correspondence there. As I mentioned, we can also take advantage of the differentiability of the neural network. So these are preliminary results, but we can start to optimize or refine an initial grasp pose to a better one according to some metric. So in this example, we're looking to maximize stress with the grass pose. So the initial grass pose is shown in blue, and it's being shifted up throughout this optimization process to the one in orange. We see that it does end up near the edges of the object where the curvature discontinuities typically do lead to higher stresses. So we can see that this is starting to work in a useful way. Of course, though, practically speaking, we probably want to minimize the stress, but this was an example of what we expect to be able to do with the differentiable network. Okay, so that was simulation of 3D deformable object grasping. And now I want to talk a bit about soft tactile sensing and its applications to industry. So let's first motivate quickly why soft tactile sensing is important. Well, tactile sensing in general is critical for any robot that depends on physical interaction and contact, and that's very much applicable to a manufacturing setting. And tactile sensing will inform the robot of sensing modes relating to shape, texture, hardness, temperature, etc. But however, physical interactions often involve environments that are delicate, and then we must ensure that the robot will keep these environments safe and keep itself safe. A solution when dealing with delicate environments is to use soft tactile sensing, which refers to the sensor on the robot being made of inherently compliant materials that naturally reduce the risk of physical harm. This is great for manufacturing settings, for example, in food settings where we're trying to pick up eggs or more delicate electronics, such as the one below. In our lab, we design an optical tactile sensor that is simple and easily adaptable and is a nice test bed for some applications. This soft tactile sensor is a membrane made of compliant silicone material. Downstream from the interface is an embedded depth camera. It's called the Camboard PicoFlex. It's the smallest commercially available one of its kind. And what it does is continuously outputs a stream of 3D point cloud readings due to it being directed at the interior of the membrane. So the camera is fixed in place with respect to the membrane by an airtight capsule and then mounted on the end of a KUKA for actuation. And we also feed in compressed air into the system. So this design was based on previous work on the soft cell by Carolyn, where she showed that using compressed air in a similar capsule can be cleverly controlled to modulate stiffness and expand as a means of actuation. So you can use that to increase the contact area and contact force on the object it's interacting with. All right, let's see what this tactile sensor allows us to do. It can allow you to, first of all, see the shape of objects through touch. For example, several 3D printed objects of known shape were pressed onto the membrane and you can sense their geometries. Here we see 2D projections of the point cloud image where the blue regions are points on the membrane that are deformed, but the yellow region are points that are deformed and in contact with the object. We found through repeated trials that this boundary error is as low as a few millimeters. Another cool experiment was to probe objects in 3D and build up a full representation. Here we see some results for objects like a cup at the top left, an apple juice bottom, and a student's face. So the face is a little harder to image because the interaction will change the shape of the face itself. But since the tactile interface is completely soft, the key is that it did not hurt the student at all. Okay, now we perform another more dynamic experiment for autonomous wiping. And because we can sense the shape of the object at every time step, we can use this to estimate the surface contours and then move along that surface. And maybe this is something that needs to be done in a factory setting, for example, to reduce human labor of cleaning the part at the very end. So in this first video, this tactile sensor lowers onto a cabinet and is able to follow the edges of it and wipe it with a cloth. As I can imagine, this can also reduce time in household cleaning, but maybe also in a factory. The second example is probably not found in factories, but because the sensor is so soft and safe, we can also use it to clean a human. So here the human has a trail of black pepper to represent dirt, and then with a damp cloth, which is different from the first one, the robot can follow the contour and even go over the kneecap, and actually end up wiping it off. So I want to emphasize that in these videos, the robot is blind and has no prior knowledge of the environment, and no deep learning is required. Okay, another experiment I want to talk about is also related to the importance of good contact geometry sensing. So this is a task that involves basic manipulation of a mixed set of objects. The two types of objects involved are cylindrical capsules and rectangular prisms. And the inspiration for this task is taken from the assembly line. And our task is defined as follows. We should lower the sensor until contact with one of these objects is sensed. And if it's a capsule, we want it to push it through some corridor and into a bin. If it's a prism, we want to rotate it such that its long edge is parallel to the table edge. And most importantly, we want the robot to perform these tasks without programming or hard coding. So we use learning from demonstration, in which I am physically moving the robot and showing it what to do. And once I perform these demonstrations, we can fit a 4-state hidden Markov model to represent what the robot has learned from these interactions and whether they can kind of parse out the different task phases. And we see that there are 2 behavioral paths that do respond to different behaviors that we want for each type of object. So after optimization of the hidden Markov model, we're seeing that the robot's able to generalize to new starting positions. And here's an example of it successfully executing the capsule pushing task through that little corridor and into a bin. It also shows generalization for the rotation task, where it lowers, this time onto a prism. And then, it's a bit hard to see, I'm sorry, but it rotates it such that the long edge is parallel to the left edge of the table. And all this was done without needing to know how to program, just me moving the robot. Okay, so this was an overview of my talk. Yeah, I guess we're out of time soon. So happy to answer any questions and also take this offline. A lot of details were removed, so thank you.